Good day to ladies and gentlemen. My name is Teo Pauter from Faculty of Bioengineering and Technology, Universiti Malaysia, Kelantan. First and foremost, thanks to ICMSN 2021 organizing committee members for inviting me as the invited speaker for the conference. So today, I would like to present a topic entitled From Waste to Wealth, Recycling Food, Agricultural and Industrial Waste as pore-forming agents for sustainable poroceramic production. This topic is based on a review articles that we have recently published in Elsevier Journal of Cleaner Productions on April 2021. So today I'm going to share with you the important outputs of the review articles. The presentations will cover introduction, overview of porous ceramic, and properties of food, agricultural and industrial waste. Next, we will look at physical, mechanical toxicity, performances and sustainability of the porous ceramic incorporated with the waste materials. Last but not least, the concluding remarks and prospect of this research topic. Let us begin the presentation. Ladies and gentlemen, you might be wondering what is food waste, agriculture waste and industrial waste? More importantly, how do the waste related with porous ceramic? In general, agriculture waste includes non-edible foods such as peels, seeds, as well as finished and semi-finished agricultural products. Meanwhile, industrial wastes are related to waste product generated at the manufacturing or production plant of various industry. Specifically, food waste is defined as any food and non-edible parts of food, including seeds and peel skins from the food supply chain. These wastes have a great potential to be utilized as pore-forming agents or PFA for poroceramic productions. Now, what is PFA and what is poroceramic? To answer that, let us look at the typical processing route of poroceramic. The first stage is waste preparations, which includes drying, crushing, grinding and sieving of the waste material. Subsequently, the clay and waste materials will be homogeneously mixed, followed by drying and finally firing process to produce the poroceramic. Several mechanisms can be employed to form pores in the poroceramic, which includes partial sintering, sacrificial, replica templates, and direct foaming. The method selections is based on the desired final characteristic of the poroceramic, such as a percentage of porosity and pore size distribution. Ladies and gentlemen, before any waste materials can be used to produce new material, in this case the poroceramic, it is essential to investigate the properties of the waste material. Well, the properties of the waste materials will directly influence the properties and performances of the final poroceramic. The chemical and morphological properties of waste materials can be analyzed by several techniques. X-ray fluorescence (SRF) and X-ray diffraction (SRD) are the most common techniques for chemical and mineralogical analysis of the waste. Through this analysis, organic and inorganic elements of the waste can be determined. For instance, the major silicon dioxide and aluminum oxide will contribute to the siliceous properties of the waste. These oxides are responsible for the formations of ceramic faces because the reactions between the silicon dioxide and aluminum oxide form stable maulite and sillimanite faces. These reactions result in porous ceramic with excellent compressive strength when the waste contains high silicon dioxide content. The presence of other oxides in the waste materials such as sodium oxide, iron oxide, calcium oxide and magnesium oxide are also considered as flux agents and promotes vitrifications during firing process of the porous ceramic. In other words, oxide contents enhance the alkaline fluxing actions and subsequently lowering the melting point of the ceramic. The mineralogical components of waste, which determine the phase transformations at higher temperature, are also important. It helps in predicting possible phase transformations during the fabrications of the porous ceramic. The thermal properties of waste materials are usually determined by thermography matrix differential thermal analysis (TGA-DTA). In TGA analysis, the total weight loss at a certain temperature determines the combustions of certain chemical components. For each waste, different percentage weight loss are associated with the endo-exothermic processes and can be related to different chemical constituents. The volatile components burn first, followed by the non-volatile components. For instance, the early stage degradations at less than 100 degrees Celsius is attributed to the evaporations of waste such as rice husk ash and kenaf. Meanwhile, a longer early stage degradations was observed for sawdust, grape seeds and cherry seeds, where moisture evaporations occurred between 20 and 200 degrees Celsius. Interestingly, these findings can be further supported by the complementary of DTA. Typical DTA curve would show the occurrence of an exothermic reactions between 80 and 650 degrees Celsius, corresponding to the burning of organic materials in the waste. This is because most organic porous materials cannot withstand high temperature. However, typical inorganic materials such as glass wool and rock wool are fragile and hazardous to health. The last endothermic reactions occur at temperature between 700 and 800 degrees Celsius. In addition to the degradation stages for the organic components, the thermal behavior of waste materials can also determine the sintering temperature for porous ceramic productions. Well, the low firing temperature for the productions of waste-based porous ceramic indicates significant energy saving. Ladies and gentlemen, several studies have investigated the physical and mechanical properties of the waste containing porous ceramic. The physical and mechanical properties of the porous ceramic are controlled by the amount and shapes of the PFA added, pore types and particle size distributions of the PFA. For instance, micrograph of porous ceramic with irregular, spheroidal and longitudinal shapes can be obtained due to the additions of graphite waste, yeast and rice husk ash. Second, types of pores. There are two types of pores, which are open and closed pore. Both pores directly increase the water absorption of porous ceramic. However, open pores are also known as interconnected pore and are responsible for lowering the compressive strength. Meanwhile, closed pores are also known as isolated pores can increase the compressive strength. Another important property of waste is the particle size distributions or PSD, which influence the porosity of ceramic. The PSD can be used to determine the fineness of the waste. In addition, the specific gravities and bulk density of the waste would also influence the weight of fired porous ceramic. For instance, it was reported that smaller specific gravities and bulk density of sludge waste indicates a reduction in the dry weight of the final porous ceramic. Ladies and gentlemen, apart from physical and mechanical properties, toxicity concern is also very crucial and important for the porous ceramic incorporated with waste material. Toxicity is a major concern because waste might generate a toxic environment due to their heavy metal content, which would be released to the environment. It is important to ensure that contaminants within the original waste materials are effectively and safely immobilized. Furthermore, the toxicity of waste materials needs to be thoroughly investigated because porous ceramic might contaminate water and produce toxic leachate, which would be drained into river, groundwater, and soil. For instance, wastes that contain chlorine and bromine needs to be avoided because they are most important factor in affecting persistent organic pollutant, which can be unintentionally produced and emitted during firing process of the porous ceramic. Next, let us look at the performance and sustainability of the porous ceramic incorporated with the waste materials. Body formulations plays a vital role in porous ceramic production. This includes the weight percentage of waste material, which is the PFA, as well as the weight percentage of clay raw materials. In general, the additions of waste increase the porosity of ceramic and reduce their weight, thereby improving the thermal insulations of the ceramic. For example, a previous study has reported that the additions of up to 5% of corn cobs can increase the compressive strength of porous ceramic. But beyond these optimum concentrations of corn cobs, the strength would decrease. Hence, it is vital to make an appropriate selection of waste as well as utilize the optimal amount to produce porous ceramic with enhanced performance. Beside body formulations, sintering temperature during the firing process would also affect the properties and performance of the porous ceramic. An increase in sintering temperature increases the crystallinity of the products and leading to complete densifications. In this research, one of the potential advantages of food, agricultural and industrial waste is their ability to lower the sintering temperature of clay products, making them stronger and highly porous. Lower sintering temperatures also enable saving a significant amount of energy in the production of the porous ceramic. Waste-based porous ceramics offer great potentials for sustainability. However, economic and environmental issues must be addressed for the commercialization of waste-based porous ceramic products. Cost estimations for fixed and variable costs can provide an overview of cost control and profitability. Firstly, the utilization of waste indicating zero cost for raw materials and safe production costs. However, cost of waste materials pre-processing or pre-treatments and energy consumptions and instrumental costs can be expected. Secondly, the use of waste as PFA in porous ceramic productions is considered a solution for waste management. The cost of waste disposal must exceed the production cost of waste-based porous ceramics. More accurate cost estimations with more details of expenses and revenue can provide reliable budget planning required for successful waste-based porous ceramic productions. Achieving zero food, agricultural and industrial waste can eliminate environmental burdens and pave the way for closed-loop productions. Ladies and gentlemen, we are almost at the end of the presentations today. Recycling food, agricultural and industrial waste for increased energy saving and green ceramic productions can be realized as an economical and practical approach to sustainable waste management, which align well with achieving sustainability in a circular economy and the UNESCO Sustainability Development Goal (SDG). In overall, the waste-based porous ceramic can pave the way for sustainable environments, expanding the economic sector, particularly alternative building materials. Most food, agricultural and industrial waste can function effectively as pore-forming agents in the productions of porous ceramic with excellent performances including the physical properties and mechanical strength. That's all from me. Thank you.